Hi, welcome to your second video on Chapter 23. We're talking about how we can use t-distributions for building confidence intervals and doing a hypothesis test for a single sample mean. Remember that the t-distribution, when we're talking about sample means, is a replacement for the normal bell curve as long as you do not have a population mean and a population standard deviation to work with. If you had those two things, then you would use the normal bell curve. If you've only got sample data to play with, then you have to use the t-distribution to account for the fact that you don't have those two population parameters, as the t-distribution allows for more variability in your answers, which is what you should have reflected in your calculations if you're estimating two population parameters. All right, so let's go ahead and take a look at a hypothesis test for a mean here. We're going back to the Trip-Hammer Road problem. It's great to look at this data a second time through a second lens. The first time we looked at this in the last video, we talked about a confidence interval. Now let's do the hypothesis test for the same data. Trip-Hammer Road is a busy street that passes through a residential neighborhood. Residents there are concerned that vehicles traveling on Trip-Hammer often exceed the posted speed limit of 30 miles an hour. Excuse me. The local police sometimes place a radar speed detector by the side of the road. As a vehicle approaches, this detector displays the vehicle's speed to its driver. The police hope that drivers will slow down if they are reminded of their speed. For the collected speeds below, do you think the mean speed of drivers exceeds the posted speed limit? Well, that's a tougher question to answer outright with a confidence interval. Let's use a hypothesis test to try and make a conclusion based upon these 23 data values that we've seen before. So we're going to say, we're going to build two hypotheses here. The first hypothesis that we want to say is that of the null hypothesis, which is, let's assume, remember, we're not assuming that the defendant is guilty here. If the defendants, in this case, are the citizens driving on Trip-Hammer Road, we're going to assume that the mean speed limit while they travel on Trip-Hammer is just equal to 30 miles an hour. The alternative would be that the data suggests the mean speed, mean population speed of the travel speed on Trip-Hammer Road would be greater than 30 miles an hour. So we've got the hypotheses knocked out. Now let's go to the conditions, which for a hypothesis test for a mean, they do not vary from a confidence interval for a mean. So first we check randomization. Is the data collected randomly? No, probably not. With how police set up speed traps, that's unlikely, but we're going to assume that, and we're going to mark that we are assuming that. So we assume the 23 speeds collected represent a random sample. Okay, so we're assuming that. Not a huge problem to assume that. All right, so let's go ahead and mention the 10% condition. That's the second of the three that you've got to check when you do inference for a sample mean. 23 cars is, we can fairly assume, less than 10% of all cars that have traveled on Trip-Hammer. Okay, second of three knocked out. No sweat. Next one we want to check here is the nearly normal condition. I'll mark that in blue because it's a new condition that we're checking for inference on means. Okay, now how do we check that? Well, we've got these 23 data values. The only way we can check whether or not these 23 data values constitutes a unimodal and symmetric distribution is to go to a histogram. Now remember that, like we talked about in the last video, the conditions that we're checking in the nearly normal condition, we've got kind of sub-conditions to look for, really are based upon your sample size. If you're looking for, if you've got a sample at sample size under 16, so 15 or fewer, then you've got to make sure that the sample data is both unimodal and symmetric. If you've got a sample size between 16 and 40, in that case, you're really checking to see basically is the sample data unimodal. So this is a question we can answer by going to the graphing calculator, and let's turn this on. let's go to Stat Edit, and we're going to enter into, I will enter into L1 here, the data that we've got, these 23 data values. So we have, and pull this to the side, I'm seeing 29, 36, 37, 29, 28, 36, 24, 31, 38, 34, 31, 29, and after that 29, we've got a 34, 30, 21, 34, 27, 31, 34, 34, 26, 32, and 29. Okay, so we've got all 23 data values entered into L1. Now we need to make a histogram of that data by going to Second Stat Plot. The plot is on, and the histogram is selected. XList is correct. The frequency is set to 1. So let's go ahead and, not second, let's do zoom. Let me quit out of this. It does that sometimes. Zoom stat. And sure enough, based upon the sample size that we had to work with of 23, because the sample size is sufficiently large, we only have to check unimodality, which we have. We've got that. We've got one central peak here. And we've more or less got symmetry as well. So we're going to reproduce this histogram below in blue here. And make sure we're clicking on the wrong or the right thing here. So we have the nearly normal condition in blue. On the vertical axis is your count. On the horizontal axis, you have the speeds. The speed in miles per hour. Okay? So let's go ahead and we've got 1, 2, 3, 4, 5, 6, 7 bins here. So let's extend out the horizontal axis a little bit. 1, 2, 3, 4, 5, 6, 7, more or less. And let's see how they measured in our calculator. Let's go hit trace. 21 to 23 and 5/6. Okay. So we've got 21 here. There's 23 and 5/6. Trace it over to the side. And we're at 26 and 2/3 here. Then we are at tracing some more. We go 26 and 2/3. Skip 29 and a half. Let's see that I'm doing this right. 1, 2, 3, 4, 5. Okay, so 32 and 2/3. Or was it 1/3? Let me check. 32 and a third. Okay. If we go 2 more to the right, we've got an upper bound of 38, making this last one an upper bound of 40 and 5/6. Okay, all right. So there are the cutoffs for those bins. It is fine for the sake of space here and for the sake of clarity and making your histogram to go ahead and skip a few of these hash marks as you go along. Not a big deal. Not a big deal at all. You're welcome to do that in the class, on the AP exam. That's okay too. All right, so let's mention the count for each of those. For that last bin, we've got a frequency of 1, backing up 1, 3, 5, 5, 6, 2, 1. Okay, so we've got 1, 2, 3, 4, 5, 6, 1, 3, all the way across there, 5, 5. Let's see, did I make enough? 1, 2, 3, 4, 5, 6, 7. I thought I did. 2, 3, 4, 6, 7. Okay, so we go to 1. Oh, I skipped the 3, didn't I? There was just 1, 3, and then 5, 5. So we're up here and making our bends. That looks good. Cut that one down across. Okay, that one's through. Then we're at 6 next, right in here. And then 2 and 1, I believe. Yep, 2 and 1. Okay, so counts of 2 here, 1 here. Cut those across. So yeah, we have reproduced the histogram. That's something that you need to do when you're talking about the nearly normal condition. Don't just give me a verbal description from the calculator. Reproduce that. So we're going to say the nearly normal condition has been met. The data is unimodal and symmetric. Okay, so that condition has been met. Now let's go ahead and move on to the guts of and the mechanics of our test. This is going to look a heck of a lot like how we did hypothesis testing for a single proportion, only now it's for a mean. So because we do not have population mean and we do not have population standard deviation, we need to work with a t-test here. All right, and the degrees of freedom, well, we had a sample size of 23, so the degrees of freedom is equal to 1 less than that, 22, and the expected value of a sample mean of size 23 should just be equal to the null hypothesis assumption, which was that everyone's traveling at 30 miles an hour. So we're going to fill that in right down here in the middle. And the standard error, because we do not have population mean and standard deviation of a sample mean, would be equal to S over the square root of n. How do we get S, the sample standard deviation? Well, let me show you here on the calculator again real quick. We talked about this in class, but I'll reiterate for you here real quick. We're going to go to Stat, Calc, one variable stats, use the L1 list, frequency list, you don't have to worry about, calculate that, and capital S sub x here is the standard deviation of the sample data. That's 4.25. Rounding to the hundredths place over the square root of 23. This comes out to be 0.886 for the standard error. Now, what's the critical value, the number that we care about in this bell curve? Well, we're going to get that critical value, the t-score here, by noting that we want to see if this sample mean of 31 is exceptional given this t-distribution bell curve. So we're going to find a t-score rather than a z-score. We're going to say t sub 22, 22 referring to degrees of freedom again, equals to 31, the sample mean minus the null hypothesis mean assumption, over 0.886. So we are at 1.13 standard errors to the right of the mean. So our p-value is equal to the probability that a t-score with 22 degrees of freedom be greater than 1.13. How do you use your calculator to find this p-value? Well, you're going to go in Wabbit to second distribution, and then you will use t-CDF instead of normal CDF. And the lower t-score that we want is, because this is greater than based upon the alternative hypothesis assumption, we're going to use 1.13 and an upper bound of like 1,000. Degrees of freedom is essential for t-CDF, that's 22. And then we'll paste that. Enter, and that is 0.135. Okay, so we got a p-value of 0.135. Let's talk about our conclusion here. And that is, we're going to conclude the same sort of thing that we would have for a hypothesis test if we were doing it for a single proportion, only now for the mean. Due to high p-value, 0.135, we fail to reject the null hypothesis assumption that the mean speed of cars on Trip Hammer is 30 miles an hour. And there you go. Not too bad. All right, so it works a heck of a lot like hypothesis testing for a single proportion. We have now, let me just talk about the distributions we've seen. We have seen a sampling distribution for sample means. We saw that back in chapter 18, and we saw that if we know population mean and population standard deviation, that's where you can use the normal bell curve. Also using a normal bell curve is a sampling distribution for sample proportions. The bell curve is used for confidence interval for one proportion, a hypothesis test for one proportion, a confidence interval for the difference between two proportions, and a hypothesis test for the difference between two proportions. So only the t-distribution is being used for confidence and hypothesis testing on means if you don't know population data. All right, that's the video. Have a good one.